Hi! For this video, we're gonna learn how to calculate for the value of the equilibrium constant. Now, on your screen, you see the steps that you need to follow to organize the process of solving for your equilibrium constant. It says here the first one is you tabulate the initial change and equilibrium concentrations of both the reactants and the products. So we can use the initials I, C, and then E. Second is we determine the change in concentrations. So this is the start of filling out the table according to the coefficients of these substances. Third is we use stoichiometry to calculate the changes in concentrations for the rest of the species that we want to know. And lastly, the moment the table is complete, we can now calculate for the equilibrium concentration value. So I will be showing you two examples in this particular video. So I want you to pay attention and please prepare your notes so you can solve them yourself. The first problem is this. It's the formation of hydrogen iodide from H2 gas and I2 gas. In this case, you're given 1 mole of H2 gas and also 1 mole of I2 gas that is placed in a 5-liter sealed flask. The mixture is then heated to a certain temperature, and so the equilibrium of this reaction has been established. Then it says that at equilibrium, the mixture has been found to contain 1.580 mole of HI. And then the questions are, you need to get the concentrations of H2, I2, and HI. In other words, the concentrations of all your substances, and then eventually you need to be able to calculate the equilibrium constant Kc. So how do we go about that? First step is we have to tabulate. But before we tabulate, you know that your concentrations are not in molarity. So because you're given mole and the volume in liters, that means you need to convert or to get the molarity concentration for every substance given. So in this case, it's written in blue. So if ever you forgot how to get molarity, please look at the previous video about molarity, your quick guide to solving for it. So in this case, just a quick run through. All you need to do to get molarity is you get the mole. So 1 mole will be divided by the volume indicated in the problem, which is 5 liter. So that's why you get these values in blue. So the moment you get all concentrations in molarity, this time we're ready to do step 1, which is we tabulate. So how will the table look like? It's gonna look like this. Sorry for this. So if you look at your screen, let's just go to the original slide for this. So if you look at the screen here, I have enclosed in red the amounts that were given. So the amounts that were given were zero point 0.2 molar for both H2 and I2. And of course, the product has not been indicated to have an initial amount. That means it is 0. Then at equilibrium, the product HI was found to have a concentration of 0.316. Now, how do we determine the rest of the concentration? All you need to do is put the variables plus 2x, negative x, and negative x. Where do these variables come from? They come from the coefficients of your balanced chemical equation. So this is just like algebra. This is to make your calculation more accurate and more efficient. So because 2hi, that means the change is plus 2x. And for H2 and I2, because their coefficients are just both 1, so the change for the reactants is negative x, indicating the negative to be the, the representation of being used up. While the positive on the other side means they're being formed and increase in the concentration. So how do we now get this excess? We know that we can readily get the difference between the 0 and the 0.316 because these are given in the problem. So the change or the difference between these two is 0.316. So therefore, we can say that plus 2x is therefore equal to 0.316. If 2x is 0.316, therefore x is divided by 2 of that, which is 0.158. This comes also from the relationship in stoichiometry. but we're doing it the shorter way, which is the same through with the negative x here. So therefore, the negative x value is also negative 0.158. You need to put negative because these are the reactants indicating that these are the amounts that were used up. So now we've already looked at the relationship of the variables and get the values of the changes. Then we can now get the equilibrium concentrations, in which all you need to do is subtract the initial with the change, so we can get 0.042 for both H2 and I2. Then we can also get, of course, the 2HI is already given in the problem. So all of these that are enclosed in green box is what we need to calculate for our Kc. In this case, Kc is bracket Hi squared divided by bracket H2 times bracket I2. All we need to do is substitute all these values. The square here is an indication that 0.042 is repeated for both substances. So dividing this, we will get equilibrium value, which is 56.61. In this case, we don't need to necessarily put the unit of our K. It's unnecessary, in other words. So this is the shortcut on how you can get the changes in the amount so you can get the correct equilibrium concentration. Okay? Now let me give you example 2. Example 2 gives us a much more complicated chemical reaction. In this case, we're given the mixture to have molar units, so this will make it easier a bit. So we got zero point 0.1 molar of NO, then 0.050 molar H2, and we got also 0.100 molar of H2O. So these are the amounts, and if you notice that one product has an initial amount. And of course, in every equilibrium problem, you must be given at least one equilibrium concentration. In this case, you're given NO, which is 0.062 molar. So how do we determine the Kc value? So we know that the table will look like this, and your Kc expression will look like this too. So we plotted what was given in the problem. That's the one in black. So zero point 0.1, zero point 0.05. Of course, the other product that's not mentioned is 0. The other one is zero point 0.1. And the equilibrium, the only equilibrium given was NO, so you get 0.062. Automatic is we need to put the variables for changes from your balanced chemical equation. Sorry for that. So in our balanced chemical equation, you have 2, 2, 1, and 2. So you get negative 2x, plus x, and plus 2x. Plus for products, negative for the reactants. So how do we now get its value? So we know that we can readily subtract your NO because you're given initial and equilibrium. So therefore, your 2x means 0.038. In this case, it's negative because it's a reactant. And so it follows that the other variables for negative 2x is also negative 0.038. For N2, because it's just x, so it's divided by 2 of 0.038, so we get 0.019. And for H2O, because we have also 2x but positive, so it's also 0.038 but again positive. And the moment we get all the red changes in concentrations, then we can get eventually the equilibrium concentrations in red. But this 0.062 is the one given in the problem, so that's why it's in black. And the moment we got all the equilibrium concentrations, then we can get our Kc value. So from our Kc expression, we substituted all the values of the rest of the variables. And again, let me emphasize that the values you're using are the values of the equilibrium only. And the moment you have that, put it here, and so we get the final equilibrium value, in which, in this case, no need to put the units for the